Hello, this is Lexi from Dr. Zarfakar's group at the University of Pennsylvania. Atomic force microscopy is an important tool we use in our research. Fakar Lab is equipped with two AFMs. Because of its high resolution and convenience to use, AFM becomes very handy when we want to check the surface status of our sample. Also, there is great science performed using AFM. In this video, I'm going to talk a little bit on how AFM works and introduce several research projects completed by AFM. AFM is a kind of scanning probe microscopy, which can tell you the properties of a sample surface, such as its topography, adhesion, and elasticity. Usually, it has a resolution of several nanometers. An AFM is composed of a cantilever, whose motion is controlled by a piezoelectric scanner. At the end of the cantilever, there is a tip, which moves along the sample surface in order to discern any change in surface height. A laser beam is used to keep track of the bending of the cantilever and is reflected into a photodetector. There is a feedback loop between photodetector and piezoelectric scanner, which tries to keep the motion of the cantilever unchanged. Surface morphology is obtained based on how much the piezoelectric scanner responds to the change of beam position in photodetector. This feedback mechanism will be explained later. Before that, I want to talk about atomic force. As a tip approaches a sample, at the beginning it feels a small attraction force, and this attraction will get stronger until it reaches a maximum. From this point, when the tip travels closer and closer, it starts to feel a stronger and stronger repulsion. There are mainly two modes in AFM, contact mode and tapping mode, which is called AC AFM as well. They work with different sample tip distance. In contact AFM, the tip will be in the repulsion region, causing the cantilever to bend. In AC AFM, the tip oscillates sinusoidally on top of the surface, mainly in the attraction region, and contacts with the surface intermittently. Now I will start with contact AFM and explain briefly how the feedback loop works. When a change in surface height is detected, the cantilever deflection will change, and as well as the position where the laser beam is reflected into the detector. Then the piezoelectric will respond to it and restore the original deflection of the cantilever. Based on how much the piezoelectric responds, the surface morphology is being measured. While in ACAFM, the tip oscillates sinusoidally at or near one of its resonance frequencies on top of the surface. When the barrier is encountered, the amplitude of oscillation will change. Topography also means how much the piezoelectric changes to maintain the original oscillation amplitude. Here I'm showing a pretty cool image collected with contact AFM. It's a calibration grid, but for most of the time, we prefer to use ACAFM in our lab because of its high resolution, and since in ACAFM the tip is only in intermittent contact with the surface, it's non-destructive to soft samples, which we usually work on. Also, ACAFM is less affected by adhesive and frictional force compared to contact AFM. As you can see here, amyloid fibrils can be imaged with ACAFM, and we can even distinguish the type of them. In Fakra Lab, you can work with contact AFM, acoustic-driven, and magnetic-driven ACAFM. You can also image in water. Now I'm going to talk about a variety of works conducted with AFM. They include fibrils, block polymers, and organic thin films. Let me start with the first one, of fibrillization kinetic. This work requires a high-resolution AFM and an experimentalist with great patience, because these fibrils are less than 1 nanometer in height. What I'm showing here are images taken after different incubation time. You can see fibril aggregation with time. The statistics of fibril length are obtained by analyzing multiple AFM images. Then, a kinetic model is proposed for this surface-mediated fibrillization, which includes monomer adsorption, monomer addition, and nonlinear elongation. By performing numeric simulation, aggregation rate constant can be solved numerically, and you see that experimental results with different solution concentration can be well fitted with this model. Other than fibrils, we also use AFM to study thin film dynamics. Isothermal duetting experiments can be conducted on one of our AFM that has temperature controlling stage. Images can be collected continuously as the film duets. By analyzing the duetted area and fit them into an empirical formula, characteristic duetting time of different film thickness at various temperatures can be calculated. You see that, as film gets thinner, its characteristic duetting time becomes smaller and shows weaker temperature dependence. Another cool thing accomplished by AFM is to use a mosaic virus to study surface diffusion of organic glasses. As the virus is introduced on top of an organic surface, a meniscus will grow due to surface diffusion. Using a simplified Mullins model, we found there is a one-fourth power law between the time and the width of the meniscus. The intersections of this meniscus are self-similar when they are treated with the one-fourth power law. Then, the surface diffusion coefficient of this organic glass can be calculated numerically. An important result of this study is that the surface diffusion of a glass is much faster than the bulk relaxation. This is the foundation of stable glass formation, which is introduced in other videos from our group. The last example I will give is a block copolymer disorder order transition after solvent annealing. On as casted sample, you don't see any typical radial correlation, while after solvent annealing of a certain time, the cylinder morphology shows up, which suggests a kind of self-assembly. Besides measuring surface topography, AFM can also be used to study the film mechanical properties. An ongoing project in our lab is to study vapor-deposited film mechanical properties by doing AFM indentation. The slope of the force distance curve indicates the stiffness of the sample. Moreover, by looking at the rate of indent recovery, surface diffusion coefficient can be derived too. There are definitely more possibilities of AFM waiting for you to explore at Fakra Lab. Please visit our website if you are interested in us. With that, I want to thank you for listening and welcome to join us.